From the time our solar system began 4.5 billion years ago, it left behind alluring traces of its early formation, debris such as asteroids and comets. Ranging in size from grains of dust to entire mountains, from football-shaped lumps to planetoids, these remnants were once the building blocks of our planets. Perhaps they even carried the initial ingredients for life itself. Now, in our modern era of exploration, these icy and rocky objects stand ready to reveal their long-hidden secrets. Asteroids are believed to be formed from chondrules, or flash-heated grains of rock within the stellar disk that gave rise to our solar system. These chondrules clumped together, forming the earliest asteroids, and ultimately the materials that would merge into planets. After the planets coalesced, plenty of leftover asteroid material remained, covering a broad range of shapes and sizes. The largest among them are sometimes referred to as minor planets or planetoids, large enough to achieve an ovoid shape. Pluto, for instance, got reassigned from major planet to minor planet. The smallest leftover fragments are typically called meteoroids. A handful of these planetoids have even wound up orbiting planets, becoming moons in the process. Although many asteroids reside in the classic asteroid belt between Mars and Jupiter, with Ceres as the best-known example, and the first to be discovered, asteroids do not confine themselves there. Many orbit much closer to Earth, called near-Earth objects, NEOs. Our first close-up look at an asteroid came from NASA's Galileo spacecraft, which flew through the main belt on its way to Jupiter. Galileo imaged two asteroids, 951 Gaspra, an S-type, or stony asteroid roughly 6 kilometers in diameter, and 243 Ida, about 15.5 kilometers across, revealing that Ida was orbited by a tiny moon named Dactyl. These discoveries hinted that asteroids are scattered throughout the solar system, not just confined to one region. Consequently, scientists grew interested in radar observations to study and map these near-Earth asteroids. Radar is a very powerful tool for investigating near-Earth asteroids, says one scientist. With radar, we can spot surface details like boulders, even when the asteroid is millions of kilometers away. Only two radar facilities, Arecibo and Goldstone, are sensitive enough to regularly scan near-Earth objects, while even the Hubble telescope would only see an asteroid as a dot of light. Radar can yield rich surface features and rotating profiles, pinpointing an asteroid's exact distance and motion. Some of these near-Earth asteroids, like 2004 BL86, revealed they carry their own moons, a reminder that the solar system is full of unexpected surprises. Others, such as 2014 HQ-124, pass relatively close to Earth and warrant careful observation to ensure no dangerous encounter with our orbital path. Asteroids come in many types. C-type, carbonaceous asteroids are the most common, about 75% of the known population. In 1996, NASA launched the Near-Shoemaker probe, the first dedicated to an asteroid mission. It briefly encountered 253 Matilda, a C-type, before heading to 433 Eros, a larger asteroid. Near-Shoemaker orbited Eros, gathering extensive data, and in 2001 landed on Eros itself, making it the first craft to do so. Another NASA mission, Deep Space One, was an experimental probe that first observed asteroid 99969 Braille, though technical glitches hampered the images. It continued on to an even more intriguing target, a comet, 19P Borrelly. Comets, regarded as close cousins to asteroids, originate from the colder, darker outskirts of our solar system. They're seen as leftover fragments from the same formative period over 4.5 billion years ago. Dr. Gerhard Schramm, referencing our cosmic heritage, notes, Comets are basically time capsules, preserving material from the birth of our solar system. Because comets can appear spectacular when they near the sun, human beings have recorded them for millennia. One of the most famous is Halley's Comet. When it returned in 1986, no fewer than 5 different space agencies dispatched an armada of probes, ICE, Giotto, Vega 1 and 2, Suisei, and Sakigake, to intercept it, gleaning new insights. In 1994, astronomers got a startling demonstration of comet power when Comet Shoemaker-Levy 9 broke apart and slammed into Jupiter, unleashing colossal eruptions visible from Earth. Scientists concluded it was time to study these cosmic ice balls more thoroughly. NASA launched Stardust, which collected dust samples from comet tails, Wild 2 and Temple 1, and returned them to Earth. Around the same time, JAXA, the Japan Aerospace Exploration Agency, sent Hayabusa to asteroid 25143 Itokawa. In a daring touch-and-go maneuver, it retrieved tiny samples and returned them to Earth in 2010. That mission took 7 years in total, with the precious sample capsule recovered from the Australian outback. In 2004, the European Space Agency launched one of humanity's boldest ventures, Rosetta. Its goal, to rendezvous with comet 67P Churyumov-Gerasimenko, place a lander on its surface, and observe the comet's changes as it approached the Sun. After multiple gravity assists around Earth and Mars, Rosetta passed 2 asteroids, 2867 Steins and 21 Lutetia, along the way. Then it arrived at its primary target. Landing on a comet nucleus is possibly the hardest thing we humans have ever attempted, said one of the mission engineers. The small lander, Philae, touched down, sending back the first images and data from a comet's surface. Despite complications, Philae briefly bounced and ended in shadow. It carried out measurements before its batteries faded. The Rosetta orbiter continued to monitor 67P from orbit, revealing precious secrets about cometary organic materials that might illuminate life's origins, asteroids colliding and deep impact. At times, asteroid collisions occur in space, creating bright new features. In 2010, astronomers spotted what looked like a comet tail, but turned out to be debris from a high-speed impact on asteroid P2010A2, dubbed 596 Sheila, with forces comparable to a 100-kiloton bomb. Earlier in 2005, NASA had done something similar on purpose, sending the Deep Impact spacecraft to Comet Tempel 1, where a kinetic impactor hammered into the comet to analyze the ejecta plume. The list of asteroid missions continued with NASA's Dawn probe, launched in 2007. Dawn used ion propulsion to visit Vesta, the second-largest asteroid, visited for 13 months of orbital study, and then moved on to the biggest, the dwarf planet Ceres. In orbit around Ceres, Dawn returned unprecedented data about its surface and possibly subsurface oceanic materials. Japan launched Hayabusa 2 with improved sampling and landing mechanisms, heading for asteroid 1999 Ju-3, Ryugu, expected to return sample material to Earth by 2020. NASA also announced OSIRIS-REx, a sample return mission targeting asteroid 1999 RQ-36, also known as Bennu. Launching in 2016, OSIRIS-REx aims to bring back up to 2 kilograms of pristine asteroid rock in 2023. These studies do more than quench scientific curiosity. In 2013, a 9,100-ton asteroid exploded over Chelyabinsk, Russia, generating a blast equivalent to 20 Hiroshima bombs, injuring 1,500 people and damaging thousands of buildings. Earth has experienced asteroid impacts before. Just ask the dinosaurs. And it's unlikely we've seen the last. Through the United Nations, major space agencies, including ESA and NASA, have established a safeguard program. They track near-Earth objects, assessing collision risks. NEOWISE data suggests we've found 93% of near-Earth asteroids over 1 kilometer in diameter. But thousands, each bigger than 100 meters, remain undiscovered. Meanwhile, experts discuss possible deflection strategies, kinetic impactors, a spacecraft slamming into an asteroid to shift its path, or gravity tractors, using a spacecraft's mass to pull the asteroid off course. NASA is even studying a robotic concept to capture a small near-Earth asteroid, towing it into lunar orbit, where astronauts could then examine it, helping us build more advanced planetary defense tactics. Every new mission, whether capturing a dust grain from a comet's tail or measuring an asteroid's mass, expands our cosmic know-how. In time, that knowledge may prove key to defending our planet from rogue space rocks and clarifying the origins of life carried within them. After all, the more we learn about our ancient neighbors, the better prepared we are to safeguard our place in the solar system,